Okay, let's continue our lecture. So we just mentioned after the MUMPS process, actually you can fabricate this kind of cross-section of the electrostatic motor. So if you want to understand the whole structure, you may come back to our lecture in the surface micromachining. So the top view of the overall structure is like this. Okay, you have a rotor, and you have a center pole and the anchor aerial, and a stator on the outside. So using the electrostatic force to drive the rotor at the center to rotate around the pole. Okay. So remember, there are some small things here, right? Looks like small hole here on the top. Actually, there are dimple on the bottom. Look, if you look onto the cross-section area. Okay, on the top, it looks like a deep hole structure, but on the bottom, actually, there are some materials extrusion under the rotor structure. So those extrusion structures are dimple structure. So the purpose is for reducing the contact area between the rotor to the bottom surface to reduce the friction problem. Okay, is that easy to understand? Okay, so when you have some problem to understand the structure here, you always can come back to here to look at this kind of structure. It's similar structure. Okay, so now after we have put down all 11 masking layers here, and also they have been defined in different zip file name and also GDS2 numbers. So those are, you can, after the fabrication design, and you can do the fabrication right away when you send out the masking material into the max fabrication vendor surface. So they are also showing different colors. You can look into your design software to check it out. Okay. So we already mentioned about the design rule. Easy design rules are 3 micron line and space, and also overlap and the border 5 micron, and distance between the holes, etching holes, 13 micron. Okay. And some important thing to understand, we list over here is to remove large area of thick poly when oxide holes not covered or polysilicon, there will be a problem. So because you want to do the deep etching, remember we are using the RE etching to etch through all the structure layer. So if you etching through the thick, oxide layer, and then without polysilicon layers, for example, poly 0 on the bottom to protect. So if you have some kind of over etching, for example, like 20% over etching, so is it possible to etch through the bottom silicon nitride surface, and then your poly 2 will contact with the substrate directly. That's a problem. So remember, if you want to remove a large region of thick poly, and the oxide hole not cover the polysilicon, so they will have this kind of problem. And the second issue you need to consider is actually the thick command is only one command to etching through from the second layer of structure layer to the first layer at once. Okay, if you want to separate them into 2 steps, for example, you do thin oxidation etching first, then thick the second. There will be some misalignment problem because you are using 2 masks for etching. So you need to do alignment twice. So there will be misalignment between these 2 masks. So if you have a large etching area and have some misalignment, the sideway can be etched through, and you also has a similar problem as before. The silicon nitride can be etched through. Okay. And another issue is coming from the pad design, because for the pad area, you need to open up a large area. And the large area, if you have the first oxide cut larger than the polysilicon 1 pad area, also there's no protection layer underneath. So the RE etching may etch through the silicon nitride layer. So in that case, you also have some problem to expose the button substrate for shorting problem. That's a third problem. And also, if you apply the thick oxide command, thick oxide cut, but no poly 2 cover on the top, so the nitride poly 0 etching can be etched away during the poly 2 etching process, and the polysilicon 2 can contact with the substrate as well. So the first 3 problems coming from the RE etching, long RE etching. The long RE etching, if you don't have protection on the bottom, it can be easily etching away the silicon nitride protection layer to get a shorting problem. So these 4 are similar, but they appear on different conditions. Okay. Number 5 is the metal. Remember, we have a chromium and gold as a metal layer, and it's not easy to survive in long HF etching process because the chromium is not a good material to resist the HF etching. So we need to try to shorten the etching time as short as possible. So usually we will apply like a couple minutes, no more than 2-3 minutes. Okay, so that's why sometimes we mention about we need to puncture an etching hole, okay, on the top of surface of the polysilicon 1 or polysilicon 2 if they are a large plate. In that case, we can reduce the etching time to preserve the metal layer. Okay, so yeah, so it's important to understand this. Okay, so those are things you need to understand. So now I will show you some of the structures which can be made by using the MUMPS process. For example, the micromirror system. So at the end, you are going to present your own project. So I know somebody has chosen micro actuator as your final project or micromirror as your final project. So here I will show you one example, so you can maybe take this into your consideration as an example for your design. So the micromirror array, actually, the mirror is over here. So on the bottom, there's a backbone to support this mirror, and the backbone can be pushed forward or pulled upward, downward. So in this case, the angle of the mirror can be adjusted according the button. You push the structure forward or backward, okay, to adjust the angle here. So in order to give a movement, so there's a need of the actuator on the sides, okay. So here I show you 2 sets of the actuator. One is in the horizontal axis, the other one is the vertical axis, in 2 different axes. So those actuators are count drive. So I will discuss a count drive actuator later on, okay? But now you just understand this kind of actuator. So the count drive actuator gives the motion of a linear motion to the direction along this axis, back and forth. Okay, actuator give the back and forth, go forward and then backward. And also this one, the other one, give the movement on the other direction, opposite direction, 90-degree direction to the first axis. So this one give the, for example, x-axis movement. The other one give y-axis movement. So the movement is go back and forth, okay? And you want to transfer the back and forth movement into a linear translation, because you want to push the mirror into some kind of angle. You are not going to do back and forth, right? You want to move continuously until the mirror stops at some kind of angle, right? So you need to transfer those back and forth movement into a linear movement. So in that case, you need the gear sets to transfer your back and forth movement into a linear translation movement. Okay. So we will talk about each individual device in more detail. So now just give an overall view. So the whole device consider the mirror structure and the structure to push the mirror, and the gear set to transfer the linear, the back and the forth movement into a translation movement, and also 2 sets of actuator to give the movement in 2 different directions. Okay, that's the basic structure. So now we go to the detail. Okay, so first we look into the micromirror. So when you look into the micromirror structure on the side, you can see several things. The first thing is that you can see we have a lot of etching holes on the top surface, right? As we mentioned before, the plate is considered large surface. You want to release the structure, you take a long time for etching if you don't design those kind of etching holes. So those etching holes can allow the etching going down to the surface to etching away the bottom superficial layer easily, okay, without only taking the etching from the sides, from the edge, but we can also take the etching from the center, from the holes, okay, to the bottom. The first thing you need to look at. The second one, you need to look into the connection. The interesting is the connection. Because you want to freely rotate the mirror, actually the connection here need to be flexible enough. So the connection need to flexible enough to allow the movement, the rotation of the mirror, but also don't want the position of the mirror change. I mean, the mirror will fix onto that position, but it can freely rotate without the translation. So that's the purpose for those connections. So there are several kinds of different connections. The first one connection is to connect the mirror to the bottom surface. Remember, if you want to rotate the mirrors into some kind of different angle, there will be poles, okay, underneath here. So the mirror need to rotate around the pole. So the pole need to be smaller than your space allowed on the bottom. Remember, we have a first structural layer, the thickness is only 2 micron, right? So that means that when you rotate the pole, the largest size of the pole need to be smaller than 2 micron. Otherwise, it's not rotatable. You'll be got stuck. Okay. So when you consider the structure here, you need to consider those information. But we will take a look at later on. Okay. So this one we will connect the position of the mirrors onto the bottom surface. So the position will be fixed, but the mirror is allowed to rotate along this pole. The second connection will be the connection between 2 plates. The 2 plates will be lifted up from the surface. So the position between these 2 pieces will be fixed by these 2 connectors. However, the 2 plates still need to be allowed to rotate. Okay. So the structure of the second connector will be different from the first one. Okay. The first one will connect the mirrors onto the surface, on the bottom fixed surface. But for this connector, we'll connect 2 plates. But the connector will need to move with the 2 plates, okay, to elevate into some kind of a out of surface area. So the design is different. We will take a more detailed look later. Okay. The third one is this connector. The connector need to connect to a translator plate. So the plate will move along this direction. So the connector is not fixed onto the surface. So it's not like the first one. So it's more similar to the one on the top. But the but the connector will still keep it on the surface, but with the movement ability along this direction. Okay, so now we take a close look of the hinge. Okay, the connector. So there are 2 hinge 1 and hinge 2. So hinge 1 is corresponding to the top hinge, okay, the connector. So when you look into the top hinge, actually you can see that the hinge has 2 structures. One is interior structure, the other one is ulterior structure. So interior structure, you can see on the 2 mirrors, there are fingers, okay, stick into the bottom of this frame structure and do the connection to the frame structure. So you can see the bone, the dog bone-like structure connect to the bottom finger belong to the left-hand side. And the outside frame, you have the other two structures pinning onto the center fingers belong to the right-hand side. Okay? So you can imagine when this structure, these two plates going up, these two structures, in frame and out frame two structure, will be locked to each other without going off. Okay? They will lock to each other. But because the structures look like a finger structure, so the finger structure still allowed the two plates to rotate, but without come off. Okay? It's not very easy to understand, so you need to have some imagination to image the action, okay, of its two plate. So this one structure, the hinge one, corresponding to the top connection. The second one, about the bottom one. So we look into the hinge 2. The hinge 2 actually is rotated already. So the mirror has been rotated up. So what you see here is the center pole is underneath the hair-like structure, the head-like structure. So when we take a draw of the cross section, so the hinge fixed onto the surface and then give a space here around 2 micron, right? Because from the first layer, superficial layer, this is a 2 micron. So now you have a pole connected to your mirror, huge mirror. There's a pole here. So when you rotate the pole need to be smaller than this size, right? Otherwise it cannot be rotated. But now we consider our design rule. Our design rule is 3 micron design rule, right? 3 micron design rule. So your smallest size of the line is 3 micron. And consider poly 1 have 2 micron thickness, right? So in this case, if you design the pole according to design rule, so the diagonal length should be larger than 3 micron. So you have a 3 micron, this kind of pole, is it rotatable? No. Okay, it's not rotatable. So that's why when we design the mirror, the pole size need to be smaller than 1.5 micron. Even you design 2 micron, okay, you consider 2 micron here. So the diagonal distance still be larger than 2 microns, still cannot be rotatable. So sometimes we need to design this into 1.5 micron or even 1 micron. So it's quite dangerous. So this size is smaller than your design rule, 3 micron. Okay. So when you do the design, actually this part is a valid design rule. So when you do the design rule checking, the design rule will tell you this is a wrong design. But it's okay, it's up to you. So like before, if you have somewhere valid design rule, you can check design rule everywhere, not and leave that area until the end. So after you finish all the design rule checker without any problem, and then try to reduce the structure of this part into the size you want. So you got only the final result, only one arrow here. I think it's okay. So the vendor will tell you the risk is on your own. Okay, you need to take your own risk. So if the fabrication is not good, the structure will be damaged. But if you don't design this way, you won't get it rotated. There's a problem. Okay, remember this. Okay. So this is the hinge 2, the second connector to connect this area, okay, the plate to the bottom surface, okay. So after understand these two important structure, then we go to next one, the driving gear set, okay. Okay, the gear set looks like this. So actually, there are two different kind of structures. First one is this is small structure. So this small structure actually, they are used to change the translation, transfer the back and forth movement from two directions into one rotation, okay, into rotation. So the rotation of this gear will be fit into the gear set, and to translate the rotation into the translation along this gear set structure. Okay, so now we look into the detail of this part. So this is the detail of the gear sets, the driving gears. The driving gears look actually the center part is here, and you can see a small structure. The frame structure is fixed on not at the center, fixed on the sides. Okay, besides this center. So you can imagine when we have some kind of action to push this structure into left-hand side. Okay, so we move the whole structure into left-hand side, so the gear will be pushed into this direction. Then we apply the other direction of the actuator, and to move the whole set into down direction. So the gear will be moved to from center to left, then go down to this position, and we're using the other direction to pull it back into this direction. And we drive another one to push down, and we go back to the original direction, and become one circle. So finish the one circle. So you combine the push and the pull, and then pull and push. This four action, so you can finish one circle of this gear action. Do you understand? You have four stroke here. So depends this side can have a push and a pull, two action. The other direction you have a push and a pull direction. Okay, so you combine these four strokes, you can finish one rotation. Okay, so you push first, then pull later, then pull the third, then push the fourth. So you can make the rotation, one circle. So these two linear, motor can transfer the linear, the back and forth movement into the rotational movement. So the rotational movement will be connected to another gear set to make a translation. Okay, make a translation. Okay, make a translation of these gear sets. Okay. So this is for the driving gears. Now we look into the con-drive actuator. So this is the focus of our later on lecture. So the con-drive actually is looks like a lot of fingers, okay, stick to each other. So between the two fingers, it forms capacitor. So when you apply electrostatic force, the potential among these two fingers, there will be attraction force, okay, among them. So distance will become smaller. So currently we have like overlap of the finger is around halfway. But if you apply potential between these two, so the overlap will become more. So the con will be stick into the end. So let's give it a movement. So we'll discuss a bit more later on. So when we apply one side, so the whole set will move on to this side. For example, you first apply potential on the left-hand side. So the whole set will be moved on to the left-hand side. Then you let it go and apply potential on the other side, the right-hand side. Then the actuator will move on to the right-hand side. So you do this back and forth, okay? So you can move the actuator in this direction back and forth continuously. Okay, so this give you a back and forth movement. That's from the con-drive actuator. So you have two sets. One set is in X direction, the other one is in Y direction. So these two sets of actuators give you back and forth movement. And through the gear sets, the movement back and forth will be translated into rotation. The rotation connect to the gear set will become a linear movement, finally. Very complex, right? Okay, so a lot of mechanical structures inside. Yeah, so this is a detail, okay? So, and also because the springs connect two layers, poly 1 and poly 2, so there's a connection here. So on the top bottom, you can also see the dimple, things, okay? So the dimples is when the spring doing the movement, we don't want the whole area of contact with the bottom surface. They will produce a lot of friction. So by using the dimple, they can protect the surface with the contact with the bottom structure to reduce the friction problem. So there's the spring joint, okay, and with a dimple structure here. Okay, I think that's a good example for you to reference. So at the end of the design, if you want to choose actuator or mirror as your final project, you definitely can consider to apply this technology in the future. So after understanding this, now we go to more detail about the con drive, because con drive is a major structure actuator want to use to give the force to drive all different kinds of devices and also structures you want later on.